So, the fundamental principle of a liquid jet breakup is given by essentially what, as you have seen, that Plato initially discovered this and Rayleigh analyzed it using the hydrodynamic stability theory. So, we will take that up here and do the analysis. Okay. So, it is also the mechanism by which, as I said, that it is a very fundamental mechanism, and you can watch it in your kitchen sink, that if you open the tap, okay, like this, and then you will see a liquid jet coming up, and then it will develop some perturbations like this, and then these perturbations will grow, okay, and then and at some point of time it will essentially pinch off and create droplets like this. Okay. So, this what you can essentially see in your own kitchen sink, and but why that happens, that will be analyzed through this thing. Once again, as you see that, as I have impressed upon you, that the actual atomization of this actual liquid jet process inside a combustor is quite involved. It is involved different kinds of shapes and sizes, but once again the whole, as you have seen, the whole philosophy of this course is that we deal with a very complex phenomena, but then we try to look into what is the basic fundamental process inside, because without that you cannot be able to, you have absolutely no clue how to or you have absolutely no way by which you can understand the more complex phenomena in a more complicated environment. So, this is the approach we are going to take. Okay. So, as you see, there are this is how the droplet breaks up, okay, and but the equilibrium state, if there was no instability, the equilibrium state of a segment of this, if I just take up, would have been and I zoom it up here, would have been something like this. It is a cylinder, right. Cylinder, and I define the surface tension of this liquid cylinder by sigma, density by rho, and the pressure inside, which is uniform throughout, by P0, and this is the surface normal which is pointing outside, and it has a radius which is given by R0. This is the equilibrium state or the steady state. But then, as you have seen here, that this does not remain steady like this. This is a base state. It actually, in reality, what happens is that when this liquid jet comes out, there are infinitesimally small disturbance everywhere present from numerous sources, noises from numerous sources that act on this jet, and this noise essentially gets amplified in certain wavelengths, certain particular wavelengths, and those creates a disturbance, those gets amplified to create certain perturbations on this nice cylindrical state. So, then we will consider the Partup state of this jet, or a smaller perturbation probably. And this is of course this is a cylinder, and this Partup state is R0 plus epsilon. Okay. This is R0, the base state, and this Partup state, radius at this sinusoidal oscillations, the maximum part of not the power maximum, but the at a certain point of time this perturbation is given by R0 plus epsilon. Once again the properties remain same, sigma, rho, P0 plus P tilde. Sigma and rho remain same, but now because this has developed some perturbations, and this perturbations has led to essentially change in the curvature. Okay. So, as a result of that, the pressure inside changes, and this Partup pressure is given by P0 plus P tilde. All right. Now, here at the initial state, so talking about curvature, let us find out how we can relate the pressure to the curvature, and that can be related by Young Laplace's equation. which is given by P0 in the steady state. Okay. In the steady state, P0 is equal to sigma times divergence of normal, which is nothing but the curvature, and this implies P0 is equal to sigma by R0. Okay. So, here the radius in this cylinder, in this steady state, this radius is R0 and the pressure is P0. So, P0, and we can neglect essentially outside pressure, you can even consider the vacuum. But by the way, the assumptions here in this it is at this point it is time to state the assumptions before we go into this. Then there is number 1, no surrounding air, number 2, no gravity. Okay. So, and this number 3 is that liquid is inviscid. Okay. So, so there is no surrounding air, then there is no gravity, and then the liquid is inviscid, and in that state essentially we can write that because the pressure P0 pressure is P outside is 0, we can write that P0 is equal to sigma times n is equal to sigma times n, and as a result the P0 is equal to sigma by R0. This is the Young Laplace equation where we essentially relate the pressure inside the liquid cylinder to its surface tension force. Essentially, to balance just like a pressure vessel, to balance the pressure you must generate like a hoop stress. Okay, and the surface tension essentially acts like that. So, whereas in this Partup state, okay, now we can, if we consider the small perturbations, as you see that we have written it as R0 plus epsilon, where epsilon is a very small quantity. So, which means that our perturbations are basically infinitesimal, that is infinitesimally small perturbations are infinitesimally small, and these perturbations essentially happen in the z direction, whereas this is r and this is z and this is z. Okay. So, we can say that now our perturbations are essentially R0 plus epsilon, and we can essentially write it like that that R tilde, okay, this we will consider the evolution of infinitesimal perturbations on the interface, and the reason is that this will, because if we keep the perturbations to be small, we will be able to linearize our equations. If the perturbations become large, then the equations will be non-linear and we cannot do the analysis. So, to make the system amenable for analysis, mathematical analysis, we will keep the infinitesimals, we will keep the perturbations to be small, and with that we will be able to do the linearized hydrodynamic instability analysis. Okay. So, we write that R tilde, that is this now the Partup columnar surface takes the form R tilde is equal to R 0 plus epsilon, okay, times e to the power of omega t plus I k z. Okay. So, of course, we see that we have assumed Partup state. Okay. So, this is essentially this we will write this as a different notation actually, or we will write this as, okay, and this is this to a different notation. So, this whole thing is essentially this E, okay, and this is our epsilon, and so this whole thing can be considered to be like this. Okay. Anyways, so and then we consider that in the z directions the perturbations has a sinusoidal oscillations, okay, and the wavelength of those, or the wave number of those oscillations is given by k, and in time domain we do not know whether it will be sinusoidal or not. It can be exponentially growing if omega is positive, it can be damping if omega is negative, and if omega is complex it will lead to sinusoidal oscillations in time also. Okay. So, which we do not know, which should come out of the analysis. Okay. And of course, here the constraint is that for the perturbation to be small, your epsilon should be much smaller than R0. Okay. And as such, essentially the omega is this is a growth rate of the instability. We can write this. and k is the wave number, the spatial wave number. Okay. And the wavelength for this is essentially lambda should be equal to 2 pi by k. All right. Now, we can denote once we have these perturbations on our on the radius. Of course, the velocity, as you have seen that the pressure has been the pressure, there is a pressure perturbations. So, u r, which is the velocity, which is the radial component of velocity, that will also have a perturbation, say of u r tilde, okay, which is the radial component of the perturbation, and u z is tilde is the axial component of the perturbation, and similarly p tilde is the Partup pressure, as you have seen here. Okay. So, u r is now essentially the radial velocity is given by u r plus the or u r 0 plus u r tilde, u z now is given by u z 0 plus u z tilde, p is given by p 0 plus p tilde. Okay. That is, these are perturbations on the base state. Okay. So, that is how it is. And then we expect, okay, then if we put these things in the Navier-Stokes equation, okay, of course, you see that there is no in this momentum we can assume the density to be constant, and if we do that, and if we neglect because this with this the terms are essentially small, so we can essentially neglect the nonlinear contributions from the perturbations, and what we do is that if we substitute u r tilde, u z tilde, p tilde, or substitute the current let us write it clearly. These are the steady state quantities, and these are the perturbations, and P into Navier-Stokes equations. Okay. And retain terms of the order epsilon, that is the small terms. Okay. Then we get the r momentum equation becomes the z momentum equation becomes this is the consequence. We can only write this because we have assumed the perturbations to be small, and that is why this nonlinear terms like the Rans terms do not come here, that you must pay attention to, and the linearized continuity equation becomes this one. Okay. Now, we have already assumed the form of the perturbation for the radius. Now, we can expect, okay, we can expect that the disturbances or the perturbations in the velocity and pressure also will have the same form of the surface disturbance. We expect that the perturbations in velocities and pressure will have the same form as that of the surface perturbation, which was okay. So, then in that case our u r tilde and u z tilde and p tilde, these Partup quantities are given by this is small this is the amplitude which is a function of r, omega t plus I k z, similar this form. The amplitude is only a function of r, while the rest is a function of z and t. Okay. Now, if we substitute these equations into the, that is, if we substitute this into the r momentum equation, z momentum equation and the linearized continuity equation, what we will get is the following. We will get the momentum equations will be in this form, that is, after we substitute this equations we will get the momentum equations to be this form. You should work it out, and I am just showing you the final results. Okay. This is the amplitude P r, because this P is only a function of r, because if you remember that u r is equal to r r e to the power of omega t u z tilde If this is so, then the z momentum equation becomes you get complex notations, because we have in z you have got I k z which you do not have in r, and then the continuity equation becomes dr dr. This r is the amplitude, whereas small r is the coordinate radius. is the radial coordinate. So, if we eliminate ZR and PR, we get the following equation for RR, and that is given by okay. Now, this one is your governing equation. Okay. So, basically this equation comes from the continuity equation as well as which has been where the different terms of pressure and Z, the pressure amplitude and the Z and the Z and the amplitude of uz has been replaced by the momentum equation. So, this equation becomes essentially the Bessel equation of order 1, okay. And it may be written in terms of modified Bessel functions of the first and second kind, that is, it can be written like as a sum of I1 Kr plus K1 Kr, okay. But as you know that as r tends to 0, where of course it is the equation has to be defined, your K1 tends to infinity. So, then this means C2 is equal to 0. As a result of that, R becomes is equal to C I1 Kr, okay. Once again, K is the your wave number which comes in the Z direction, all right. So, now that we know that your R is given by the Bessel functions of first kind, we can obtain a pressure also like this. Okay. And so, we have got the this RR, the amplitude of the surface fluctuations and the amplitude of the pressure fluctuations in the radial directions as the Bessel functions of first kind, okay. And now what we need to know is that but we have basically in these things we have basically these constants are there. So, to eliminate the constants we need the appropriate boundary conditions. So, what can be a boundary condition? The boundary conditions can be that if this was the Partup state, the velocity of this surface is essentially equal to the UR velocity, okay. So, once again this velocity here V is equal to UR, okay, and that V is nothing but your d r tilde dt, okay. And so the boundary condition is this, that your dr tilde dt is equal to your UR tilde. We approximate it like this, and then with this we can find out the constant C to be essentially is equal to E omega times I1 K R0, okay, fine. And then if you do this the pressure balance, I will not go into that, and then we can obtain this the pressure perturbation solution explicitly, which is given by this thing epsilon sigma by R0 square and 1 minus K square R0 square times e to the power of omega t plus ikz, okay. This we can get. Now, next is the very important thing, that is our entire goal of this analysis is to obtain the dispersion relation. What is the dispersion relation? Dispersion relation is the expression for your omega, okay, that is the growth rate. So, the growth rate is a relationship of the growth rate omega in terms of the wave number k. So, we get the dispersion relation for omega or growth rate in terms of k, and that is given by, you can solve it yourself, it is very simple. Just algebra, even though this equation might look intimidating. This is the most important term. The whole equation is important in terms of quantitativeness, but qualitatively this is the most important terms. Why? Because you see our R, the perturbation R, okay, this was given like this, epsilon e to the power of omega t plus I k z. Okay. So, if omega is positive, it means that the growth rate, okay, if omega is positive, then this R will have an exponential behavior. So, it will continue to increase, okay. Whereas, if this omega is negative, it will have a damped behavior, whereas it will be unstable if omega is complex. So, now you have a dispersion relation omega square is equal to given by this thing, and all these things are positive. The only thing that can be negative is this one, that is omega square will be less than 0. This means omega will be will have imaginary component if k r 0 is less than 1. This means this is the condition for which unstable modes are possible. Of course, we know from experience that this liquid jet can never just diverge into these perturbations can never grow infinitely large. So, that is an invalid condition. It can damp down or it can happen, it can be unstable. Okay. So, under what conditions it can be unstable? It can be unstable if the disturbances, if the wave number of the disturbances times the radius, the steady state of this unperturbed state radius is less than 1. Okay. So, of course, we can then plot this thing, and if we plot this dispersion relation as k r 0, we will find that, so only less than 1 conditions are important. So, it has a plot like this. This is 1 and it maximizes at a value of, if this is 0.6, this is 0.8. So, this is the maximum value at which it attains, okay. And this value which gives, and this is my omega actually. So, this is omega by k r 0. So, omega is max when k r 0 is equal to 697. Okay. So, that means when k r 0 is equal to 0.697. So, for all k r 0, k times r 0 less than 1, omega is unstable. Okay. And of course, if you just the plot this part is also actually important. So, so if you just plot the the real part of it, you see that this is max when Kr0 is equal to 0.697, and this means that the growth rate will be maximum when Kr0 is equal to 0.697. Now, what does that mean? K is of course your 2 pi by lambda, which is lambda is better because lambda is the wavelength. So, essentially this perturbations when you have, then this is the wavelength lambda. Okay. So, this means that when 2 pi by lambda times R0 is equal to 0.697, then the omega is maximum at that lambda. So, then that lambda is given by, or if we call that lambda max, that is given by (9.02) R0. Okay. So, now you see where the 2 pi comes from. This so, if you just put this, the 2 pi essentially comes from this criteria, that if we just take any lambda and we write that 2 pi by lambda. So, the criteria for this jet to be unstable essentially is 2 pi by lambda times R0 should be less than 1. This means that your lambda should be greater than 2 pi by R0. So, for all 2 lambda greater than 2 pi by R0, as long as the lambda, the perturbation wavelength, is greater than the circumference of the jet becomes unstable. Okay. So, of course, that is the thing, and of course, it maximizes when lambda is equal to 9.02 times R0. So, using this we can even have a breakup, we can have breakup time for the jet, and that we can obtain as if we try to introduce a time scale. So, what we have obtained is that the fastest growing mode, or the maximum the fastest growing mode happens when Kr0 is equal to 0.697, and that corresponds to a lambda max of 9.02 R0. Okay. And if we correspond the time scale, the T breakup is equal to 1 by omega max, then that becomes essentially 2.91 square root of rho R0 cube by sigma. Okay. So, if you take a water jet of 1 centimeter radius of diameter, so if a diameter of a water jet is 1 centimeter, then this T breakup is about 1/8 seconds, which is seems pretty consistent from our own experience. Okay. So, this much is a Rayleigh-Plateau instability, and this is the fundamental mechanism by which a liquid jet breaks up even in absence of any quiescent air, even in absence of gravity, even when there is no viscosity in the liquid. So, that means that a liquid jet is inherently unstable because of the surface tension forces that is present in the jet, and when that competes with this, it is a competition between pressure, surface tension forces and inertia forces that leads to the breakup of this jet at a characteristic length scale. Okay. So, then we will go into fuel injection. Okay. And so, now coming back to the practical gas turbine engine, where essentially you need you have to have something like this, where you send out the liquid jet and you expect that the liquid jet will break up because of this fundamental Rayleigh-Plateau mechanisms, because of other Kelvin-Helmholtz instabilities, Rayleigh-Taylor instabilities, because of atomization. You need to create fine droplets. So the purpose, so as a engineer, you have to then manufacture, or you have to select atomizers, or you have to select a proper fuel injection devices through which you can inject this these liquid fuels. Okay. And one more thing is that one more thing that you have to keep in mind is that there can be different kind of injectors available, but these injectors there are multiple conflicting requirements. Number one, you need to have very small droplet sizes on one hand, but at the same time if you want to use too small sized orifices, because of course you see that the smaller the jet, the smaller the droplets will be produced. So you from here itself you can understand that given this analysis, that if you have very small sized, if you have a cylinder which is of very small size, then then the size of your then the breakup length, that this lambda will also be small. Okay, because your lambda max is directly proportional to the R0. So what is happening is that you are creating this, say this is the largest perturbation that is happening on your liquid jet. Okay, and this is the perturbation that is happening on the liquid jet. Now where will it pinch off? It will pinch off at this point. So essentially this lambda, okay, this whatever volume of liquid is contained in this lambda will become a droplet. So after it breaks up, in the next step can be like this. So if I just show you like what is going to happen. So this liquid jet is like this. Okay, in the next step it can be formed these things. Okay, and then it can form droplets like this. Okay, in different times. So this lambda, the amount of liquid contained in this lambda will become a droplet. Okay. So clearly if this lambda is small, if this, but it will, you cannot have arbitrary small lambda, because then it will not break up. So this lambda max, typically it is 9 times, or this 9 times this radius of this liquid jet. Okay. So this droplets that we will get eventually should be proportional, this droplet size or this d should be proportional to your R0. Okay, somehow. So what you get is essentially, if your liquid jet is very thin, if it is small in size, then you get a very small droplets, right, obvious. But so to make small liquid jets, what you have to do is that you have to use very small orifices. Okay, your orifice should be very, very small. How, but of course physically you cannot make orifice very small. Suppose you want to make it 1 micron. But the problem is that some impurities will get unclogged in this 1 micron orifice practically. So that is a problem practically. So you can have a theoretical result, but to convert that into reality, you need to put some more, you need to do some more engineering so that it can be practically implementable.